please turn to page 10 in your notes packet. Enthalpy. So far we've talked about Q reaction, which is the amount of heat. Now that we are in enthalpy, we can use enthalpy to talk about when a reaction is at constant pressure, it is going to have the same value of delta H as it has Q. So therefore we can say that delta H equals Q sub P. The sub P stands for constant pressure. Really it means nothing to us because everything we've done is at constant pressure. So really we are now just saying that instead of solving for Q, I can solve for delta H. We will explore further that delta H is the difference in the heat content, the amount of heat between the products and the reactants, and we will be using this formula in a few days. Going on, so we have always looked at whether or not something of heat or energy, which is heat is a form of, whether or not it is endothermic or exothermic. So here in these two diagrams we will see that when we have greater enthalpy of reactants than products, our delta H is less than 0, making it exothermic, okay? Or delta H is negative, same thing as less than 0. And when the enthalpy of the products is greater than the enthalpy of the reactants, we have delta H is greater than 0. We call that an endothermic reaction, or delta H is positive. Here you see a summary. We have already talked about direction of heat flow, whether it's endo or exo, Q value, whether it's endo or exo. We looked in the very beginning about the potential energy of products versus reactants, whether it's exo or endo. We looked at delta E, whether it was endo and exo. And now, today, we are adding the delta H piece. So if you have a delta H less than 0, it's going to be exothermic. If you have a delta H piece greater than 0, it's going to be greater. If you have a delta H value greater than 0, it's going to be endothermic. You will need to add this piece that I'm starring in red to the bottom of page 10, right underneath the summary table. Pause this taping and add that, please. Welcome back. Okay, so we are going to start to look at a problem here. What we have here is a relationship, after we read this, between the amount of energy and a mole. If you look at this problem, it tells me that 1 mole of methane equals 890 kilojoules of energy. Now, remember, every time we write a kilojoule down, next to a number, we need to consider whether it's positive or negative. It says releases heat, therefore it needs to be negative. So we now know from this first sentence that 1 mole of methanol, 1 mole of methane when burned is equal to a release of 890 kilojoules of heat. But we want to know how many kilojoules of heat would be released if it was 5.8 grams of methane. So then we take 5.8 grams of methane. To get rid of grams of methane, we're going to use the periodic table, or the molar mass. So 1 carbon at 1201 and 4 hydrogens at 4.04 is 16.05 grams of CH4 for every 1 mole of CH4. So grams of methane cancel, now I have moles. But we know something new. We know a relationship that we see right here. We see for every 1 mole of methane, there is a release of 890 kilojoules of heat. Okay? So, as we do that math, we will get the answer. I'm going to pause the video on my end for just a moment to get my answer key so that I don't have to pause, do all the calculations on the video. One moment. Alrighty, so I am back, walked over, got my key. So therefore, if we do the math, we're going to multiply the numbers across the top, multiply numbers across the bottom, and with sig figs we get negative 320 kilojoules of methane.